14.4 binomial probability. A coin is weighted so that the probability of getting heads is 2/3, so it's like a trick coin. What is the probability of getting exactly 2 heads in 5 tosses with this coin? All right, so what we can do here is think, okay, we're going to toss this 5 times, so we need to get 5 different numbers here, 1, 2, 3, 4, 5. All right, the probability of getting heads exactly 2 times. All right, well, the probability of getting heads 2 times, let's see, we could have 2/3, right? 2 out of 3, there's a probability of getting heads 1. So this is for heads. A probability of getting heads again, that's 2/3. And then if we want tails for the rest of these, that's 1/3, 1/3, and 1/3. And we can multiply all of these together. So when I multiply these together, let's see, that's 2 to the second, so that's 4 on top. And let's see, that is 3 to the 5th power on the bottom there. So 3 to the 5th power is going to give us 243. All right. So what you actually start to notice here is that when I am calculating this probability, the probability of getting exactly 2 heads in 5 tosses is going to be this special probability here that we have of 2/3 squared times 1/3 to the 3rd power. This was for heads, 2 heads, right? We want 2 of them. This is for tails, and we want 3 of them to occur. And then we will multiply this really by the different ways this can occur. So this could occur a few different ways, right? We could have heads here and heads here. So we need to account for the different combinations we could have. So we're going to have 5, 2 here. We're going to do 5, choose 2. So we're going to get, we can use our calculator for this part, 0.1665, or 16.5% chance of this occurring. And this is what we call our binomial probability. So this is all the ways it can happen. And these are the probabilities, and this is how many of them I want to show up. So this is the probability of heads, and this is how many heads. I want 2 heads. This is the probability of tails, and this is that I want 3 tails. That's kind of where that came from. So a binomial experiment is going to be one in which there are two outcomes, one that we call our success and one that we consider our failure. So we wanted to get heads here for those, and the other would be considered the failure, what happens if I don't get heads. An experiment has 2 possible outcomes, S and F, for success and failure, with probability of success being P, the probability of failure being Q, or we can think of it as 1 minus P. So basically these probabilities need to add up to the whole thing. It's either going to be one or the other, and when we add them together, it should be 100%. The probability of getting exactly R successes in N independent trials is going to come from this special formula here. So we have our combination, and then we have the probability of success, and then our probability of failure. Not necessarily that it's a bad thing, just that we don't get the other thing to occur. All right, so the name binomial probability is pretty appropriate because it has a lot to do with that binomial coefficient. Remember, we had that number in the front. That was our combination, really, formula there. And then it looks kind of like the terms when we were doing our binomial expansion. All right, so let's take a look at an example here. We have a fair die, just meaning it's not weighted. It's rolled 10 times. We want the probability of each of these events below. So the first one we want is the probability of getting exactly 2 rolls that are 6s. Okay, so we want the probability of exactly 2 6s. 2 are 6s. Okay. So in order to do that, we need to use our combination. So we are going to have 10, right? There's 10 times that we are doing this. We are choosing 2, 10 choose 2, and 2 of those times we want to get 6. Well, the probability of getting 6 is 1 over 6, and we want 2 of those. That means the rest of the time we have a probability of 5 out of 6, and we want 8. 2 and 8 have to add to this 10. And 1 6 and 5 6 have to add to 1. And then from here we can use our calculator. Remember this, we can go into math and then go over to probability and choose the one with a C. And obviously, the rest is just multiplication. It's going to give us about, let's see, 0.291, or that's going to be about 29.1%. Either of these is perfectly fine. At most, 1 roll is a 6. Okay, so we want to think about what that actually means. So if at most 1 roll is a 6, that means 0 or 1 roll is a 6. Because if we have any more than that, then that doesn't fit kind of our criteria here. So really we have a couple of things going on. What this means is 0 or 1 here. So we can add these probabilities together. We can do the probability of 0 are a 6 or is a 6. And we can do the probability that 1 is a 6. All right, so let's think this through. We have combination of 10. We want none of them to be a 6. So that'll be 1 out of 6 to the 0, and the failure 5 out of 6 to the 10th. Remember, 0 and 10, that has to add up to 10. Plus, and then of this we want 1 of them to occur. That's 1 out of 6. We want 1, and 5 out of 6 we want that to add to 10. So 1 plus 9 is 10. Again, calculator for this one. We're going to get, let's see, this is about 0.161506. Let's just kind of give ourselves some extra decimals here. 0.323011. And then when we add that all together, it's going to give us about 485, or 48.5%. Okay. How about that at least 2 rolls are 6s? So at least 2 really means that we're saying 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. And that's kind of a lot here. So it's probably going to be easier to think about the complement. So the complement of this would be that 2 or, well, this is saying 2 or more. So we would want 0 or 1 is 6. That would be the complement here. And we actually already know what that is. So we're going to do 100% minus, or 1 minus. The decimal form is fine. So that's going to give us, let's see, about 0.515, or that'll give us 51.5%. And we're just using our complement here. Okay. Example 2, a certain viral disease is known to have a mortality rate of 80%. This drug company has developed a drug that claims to have an effective treatment for the disease. In clinical tests, the drug is administered to 10 people suffering from the disease. 7 of them recover. What is the probability that 7 or more of the patients would have recovered without treatment? All right, so what does that mean, 7 or more? So 7 or more means 7 or 8 or 9, or there were 10 people we were looking at in total. Okay, so if we want to find the probability that 7 or more occur, we need to add all of these together. So the probability of 7 out of 10 recover. We need the probability that 8 out of 10 recover. We need the probability that 9 out of 10 recover. And we need it out of 10 out of 10, which means all of them recover. And whatever we get for these, we're going to just add all of them together. Okay, so whatever we end up getting, we'll add them all, and that should equal our answer. Okay, so let's figure these out. So the probability that 7, so we have 10 in total. We want 7 to occur. Let's see, the probability would be, what did we say, 80% mortality without this special treatment. So that means that's a failure, right? We want recovery. So 0.20 would be the other part, right? If we have 100% minus 80%, that should give us 20%. So let's see, we want 7, and we need to add 10, so that'll be 3. 7 plus 10 is 3. Or sorry, 7 plus 3 is 10. And 80% failure. Okay, this would be 10 choosing 8, and this would be an 8 up here, 80%. Let's see, 8 plus 2 is this 10. All right, 10 choose 9, 0.20 to the 9. 9 plus 1 is 10. And let's see, 10 choose 9, and that's choose 10. Sorry, I'm on the wrong one. We want 10 to recover. Let's see, that's 0.20 to the 10th power, which means we don't need any of the other one. All right. We could use our handy-dandy calculators for these. If you want to do them in parts, that might not be a bad idea, just so that you can kind of keep track of it a little. There's a lot of zeros going on with these problems. Whoops, that's a 3. 7. This is going to give us 0.0000041. The next one has 0.6 zeros. Oh my goodness. 1, 2, 3, 4, 5, 6, and a 1. Okay. Then we're going to add all of these up as best that we can, and that solution is going to give us 0.000863, something like that. So that means we still have a 0.08643% chance of that occurring. That's pretty terrible chance. So does this drug appear to be effective? Let's see. The probability that 7 or more patients would have recovered, right, is less than 0.001 that they would have recovered on their own. I mean, this is the recovery rate without treatment, right? Recovery without treatment. That's pretty terrible. So it's pretty unlikely that they're going to just get better on their own. I mean, look, that's the percentage. I don't even need to move the decimal twice. I've already done it. It's way less than 1% chance that without the drug they're going to get better. With the drug, 7 recovered. So I would definitely say that this looks very effective. So yes, I mean, without treatment, they have a very low chance of recovery. Okay.